Today we're going to focus on the system and the surroundings, and this is in terms of thermochemistry. Thermo meaning heat, thermo, heat, chemistry, obviously chemistry, the study of matter. Okay, so specifically the study of matter in relation to heat. Okay, so the system is the part of the universe on which we wish to focus our attention. In the world of chemistry, the system is generally the chemical reaction. Okay, so if we have 2H2 plus O2 gives 2H2O, then the system is all of the hydrogen molecules, all of the oxygen molecules, and all of the water molecules. The system consists of the molecules which are reacting. The surroundings is everything else, the rest of the universe. So for example, say the above reaction is happening in the gas phase, then the walls of the container are part of the surroundings. So think of it this way, if you are the system, that is the chemical reaction. So if you are the system, the chemical reaction, as you look outward, everything else is the surroundings. And in thermochemistry, we are looking at the transfer of heat between the system and the surroundings. And the universe consists of absolutely everything, the system plus the surroundings. Okay, so the universe is everything, the system plus the surroundings. So the system, in this case, could consist of either the flask and the contents, or it could just be the contents of the flask, and perhaps the flask could be part of the surroundings. Okay, so that's what we mean. Some chemical reactions or systems release heat to the surroundings. If they release heat to the surroundings, what kind of reaction are they? Are they exothermic or are they endothermic? Well, if they release heat, the heat exits the system, and so that is an exothermic reaction. If you were part of the surroundings, so if you were touching that flask, and remember the contents of the flask are the system, and your hand, if you put a hand on that flask, okay, and you felt that flask, I know that's a wonderful hand, okay, it's got like 7 fingers or something. Anyway, so if we had that hand and it was touching the flask, and we had an exothermic system where heat exits the system, what would your hand feel like? Would it feel warmer or would it feel colder? It would feel warmer. Okay, so it feels warmer. So the temperature would increase. Now remember, what is temperature? Temperature. Temperature is a measure of something. What is it a measure of? It is a measure of the average kinetic energy. And what is kinetic energy? What does kinetic mean? Kinetic means the energy of motion. So if we have an exothermic reaction, remember we have taken, in an exothermic reaction, we have taken potential energy, which is stored in the chemical bonds, stored in the chemicals, and we transform it into kinetic energy. Okay, and that kinetic energy, starts the particles moving faster. And if the particles of the system are moving faster, imagine that the particles in here are moving faster. Well, they're going to bash into the side of the flask. And as they bash into the side of the flask, those flask molecules are going to jiggle faster. And as they jiggle faster, they're going to bash into the molecules of your hand. And as they bash into the molecules of your hand is going to, the molecules of your hand will be moving faster, and so it will feel warmer. Okay, and same thing, if there were any air particles surrounding that flask, they would also get hit by the faster moving particles of the flask, and then they in turn would move faster, and that would mean that the temperature would increase. Okay, so that's an exothermic reaction. Now, some chemical reactions or systems absorb heat. Some chemical reactions or systems absorb heat from the surroundings. Now remember, when they're absorbing heat, they are taking kinetic energy and they're transforming it into potential energy. So the particles were moving faster, and if they were moving faster, their kinetic energy is greater. And if the kinetic energy is greater, the temperature is higher. And they're transforming it into potential energy. So they haven't actually lost energy, but now it is stored energy. So they're moving more slowly, but they have more energy stored in them. That means the temperature is going to get lower. Okay, so we absorbed heat, but the temperature gets lower. And remember, that's because that heat gets absorbed and it gets turned into potential energy. So it's no longer the energy of movement. People always hear, oh, it absorbs heat, it must get hotter. But it absorbs it and it transforms it. Don't forget that part. That's huge important. So these are endothermic reactions. Okay, and you guys are going to do this worksheet here. Okay, and I'm just going to go and find our other thing that we're going to do today. It's quite a short lesson today, I hope. Oh, there we go. Yep. So this is the second part of today's lesson, and that's from that bye is from last day. So we'll get rid of that because we're not saying goodbye yet today. Enthalpy. Enthalpy is a word you're going to hear a lot in grade 12. Okay. Enthalpy can be thought of as the chemical potential energy. That is actually an incorrect definition, but for the purposes of Chemistry 11, it works really, really well. Okay, so we're going to stick with it, even though it's not technically an awesome definition of enthalpy. I guess they weren't happy to have E stand for enthalpy because E stands for energy. E for energy. So they needed some other letter for enthalpy, and so they gave it the letter H, I guess because it's in the middle of the word. So enthalpy has the symbol H. We also use the Greek letter delta. Okay, that's that triangle. And delta, hopefully you're familiar with, it means change in. Okay, so we are often concerned with when the potential energy has increased or the potential energy has decreased in a chemical reaction. Are the products storing more energy than the reactants, or are they storing less energy than the reactants? So when we are looking at a change in potential energy, remember in Chem 11, we are thinking of enthalpy as the chemical potential energy. So if we're looking at a change in potential energy, we are looking at a change in enthalpy. And because delta means change in, we're going to give this thing the symbol delta H for change in enthalpy. Now let's remember, in an endothermic reaction, heat enters the system and is transformed into potential energy. So we used to have some potential energy in our reactants, some kinetic energy enters, and it's transformed into potential energy. So our potential energy is increasing. Potential energy is increasing. Enthalpy we can think of as potential energy. So enthalpy is increasing. And if it is increasing, the change is positive. So for an endothermic reaction, the change in enthalpy is positive. We've gone from having lower potential energy to having higher potential energy. In an exothermic reaction, we have potential energy within the chemicals. We go from the reactants having more stored energy to the products having less stored energy. Okay, so we have the reactants have more stored energy and the products have less stored energy. And what that means is we have gone from having more potential energy to less potential energy in the chemicals. And so our potential energy has decreased. And if it is decreased, our potential energy, remember enthalpy, we're thinking of it as potential energy, our enthalpy has decreased. And so the change in enthalpy, we've gone from higher potential energy to lower potential energy. That was a decrease that took us from a higher value to a lower value. So the change in enthalpy is negative. Delta H is negative. Next year, you're going to hear a lot of talk about the heat term. Okay, the heat term is the heat is released to the surroundings as kinetic energy. So this is going to be in kilojoules, okay, because joules are the unit of energy, and often we express it in kilojoules here. Okay, what kind of a reaction is this if we have had heat released to the surroundings as kinetic energy? The heat has exited the reaction. It has come out of the reaction. Okay, see, it's not going in, it's coming out of the reaction. So this is an exothermic reaction. Remember, perhaps over here we had, let's just say 20 kilojoules. Whoops, that's the wrong way to write a J. Kilojoules of potential energy. And then we finish with, let's say, 15 kilojoules of potential energy in our CO2 and H2O. And what would that make our heat term? Well, our heat term would be 5 kilojoules of kinetic energy. And remember, the more kinetic energy you have, the particles are going to move faster, and the faster the particles are moving, the temperature is going to be higher. So we often refer to the kinetic energy term in the reaction as the heat term. Okay, that is our heat term. So if the heat term is on the right, it's exothermic. If the heat term is in the products, the system released heat, and that is exothermic. And if it's exothermic, tell me now, is our change in enthalpy and remember enthalpy is the potential energy, is the change in enthalpy positive or is it negative? If we've gone from higher potential energy to lower potential energy. Yeah, our change is going to be negative. So the delta H, the change in enthalpy, is negative. Okay, so we can draw an enthalpy diagram for this. Okay, so you can label the x-axis enthalpy H, but you will also often see it drawn as potential energy, and we'll write that as kilojoules. Okay. Now, we start with I think this is octane. Yeah, that's octane. Okay. We start with our octane and our oxygen, and they have a higher potential energy value. Okay, so we can see that's higher. And we finish with the CO2 and H2O, and they have a lower potential energy value. So we have higher enthalpy, and our products have lower enthalpy potential energy. And if we, oh, sorry, this is higher potential energy. If we dropped in potential energy, remember the total energy must remain the same. And therefore, some of that potential energy was transformed into kinetic energy. Okay? So some is transformed into kinetic energy. And that kinetic energy comes out of the reaction. So if we were to just write this as A going to B, reactants going to products, our kinetic energy would be over here. Our kilojoules would be over on the right. Our heat term would be on the right. Okay, and we can label delta H on this reaction. Man, I've made a mess of this, haven't I? But here is our delta H for this reaction. You notice it starts high and finishes low. And if it starts high and finishes low, then delta H is negative. So we know that the reaction therefore must be exothermic, right? Because if potential energy starts high and ends low, we must be transforming some of that into kinetic energy, which means we have heat released. Okay, so this kinetic energy here, we have heat being released. So we're exothermic. And therefore, if it's exothermic and heat is being released, that's going to be transferred to the surroundings, and the temperature is going to increase. We have more kinetic energy. Temperature is a measure of kinetic energy. There are two ways to write a reaction to show that it is exothermic. First of all, we can either write the heat term on the right-hand side of the chemical equation to show that the heat is a product. Okay, so in any exothermic reaction, we can write the heat term in as a product. And you'll notice that we have a plus here. That doesn't mean that that's a positive change. It just means that it's one of the things that comes out. Okay, we have 16 carbon dioxide, which are produced by this reaction, and we have 5,076 kilojoules, which are produced by this reaction. And they are both coming out of this reaction. So there we are. Okay. We can also, if we don't want to write the heat term in the equation, we can also write it outside the equation by writing our delta H. By writing the delta H, the change in enthalpy. Remember, that means change in enthalpy. So our change in enthalpy, remember enthalpy is potential energy. These guys would have more potential energy. These guys would have less potential energy. Why? Because they transform some of the potential energy into kinetic energy. Okay, kinetic energy. And so our potential energy, so the change in potential energy is negative 5076 kilojoules. So our change in enthalpy is negative 5076 because we have dropped in potential energy. Here's a different reaction. Look, now our heat is a reactant. Okay, so we're going to take some kinetic energy and we're going to transform it into potential energy. So we're going to start with lower potential energy, lower enthalpy, and we're going to move to a higher potential energy or enthalpy. Okay, so heat, kinetic energy, is being absorbed from the surroundings, absorbed from the surroundings, and converted into potential energy. And you'll notice we start, if this is a potential energy graph or an enthalpy graph, we start low and we finish high. So the difference between them is a positive difference. We had to add in some potential energy by transforming kinetic. Okay, this kinetic energy is transformed into potential energy. And if delta H is positive, we know that the reaction is endothermic and the temperature must, now remember, what happens in an endothermic reaction? What happens to the temperature? We absorbed heat. But remember, we didn't just absorb heat, we absorb heat, and what happens to it? It transforms into potential energy. Okay, now it is stored energy. It's not energy of movement anymore. So the particles will move slower, and so the temperature is going to get lower. I guess I should say decrease. That would be better grammar there. Okay. So in an endothermic reaction, the heat term is written on the left side, the reactants side. Or you can write the delta H beside the equation. Okay, so you can either have your heat term here, it's going in, okay, it's entering, so it's endothermic. Heat enters the equation. Or we can write it as being a positive value because we're transforming this into potential energy, so we'll have more potential energy than before. Okay, and then we have some exercises, which again, I'm going to leave for you, but just before I leave you, let's summarize. Summary. Exothermic. Delta H is negative. The heat term is in the products. Okay, so that would be like A goes to B plus however many kilojoules. And then finally, what's going to happen to your graph? Is your graph going to go up or down if we have potential energy here? Are we going to start high and finish low? Or are we going to start low and finish high? We're going to start high and we're going to finish low because delta H, which is from where we started to where we finished, is negative. Okay? In an endothermic reaction, delta H is positive. We have increasing potential energy. The heat term is in the reactants. Okay, so we would have A plus kilojoules gives us B. And then finally, if we were to draw our graph, you would see that, whoops, that shouldn't be way down there. There we go. This is our delta H is positive. Okay, there's our potential energy. And there we go. I have to say, I've had a really lovely time teaching you guys this year. This is our last lesson of the year. And so that previous worksheet and then this one are your last two things you're going to do this year. Don't give up now. This will be super helpful if you're taking Chem 12 next year. And by the way, if you're not taking Chem 12 next year, I don't really care if you do this or not. But if you are taking Chem 12 next year, definitely do this because it's going to be so helpful for you. Okay? Um, like I said, it's truly been a pleasure. I love each and every one of you. It's been super, super fun. And you guys have yourselves a very, very awesome summer. And thank you for sticking with us. And that's it. Bye.